acid. So I want to label the hydrogen sulfate polyatomic ion as an acid. And now we therefore know that water must be a base. In the Bronsted-Lowry theory, we must have one acid and one base on the left-hand side, and will form a conjugate acid and a conjugate base on the other. So, with this pattern, HSO4 negative, if it acts as a proton donor, it forms a conjugate base. If I remove the proton from sulfate, I go down 1 unit and form SO4 minus 2. And the proton that the acid donated went to water. Water gains the proton and becomes hydronium, H3O+, and that would be labeled as the conjugate acid. Hooking together the conjugate pairs so you can see them. One conjugate pair is HSO4 negative 1, forming SO4 negative 2. The acid formed its conjugate base by losing a proton. The water acted as a base. Therefore, it must form a conjugate acid. When a base gains a proton, it becomes one more positive, giving us the hydronium ion. So we've labeled the acid-base conjugate pairs and hooked them together by brackets. Let's consider the same beginning point with the hydrogen sulfate polyatomic ion being placed into water. But this time in our equilibrium, we're telling it to act as a base. In the previous example, we labeled it an acid. This time we'll label it a base. Therefore, water must be acting as an acid. We must have one acid and one base on the side of the equilibrium. Therefore, when HSO4 negative acts as a base, it loses the proton, and therefore acids are formed. And water, acting as an acid, must form its conjugate base. So, if a base is a proton acceptor, beginning here with the HSO4 negative, let's place on one more hydrogen, forming H2SO4, going from a negative 1 to a neutral molecule. The water, acting as an acid, is a proton donor, and when it loses a proton, it forms the hydroxide polyatomic ion, the base ion. So thinking about our conjugate pairs, when a base accepts a proton, it forms a conjugate acid. When an acid loses a proton, it forms its conjugate base, OH negative 1. What we've just described is called amphoteric. In one situation, the HSO4 negative acted as an acid. Here's a situation where it acted as a base. Water in the original equation acted as a base, and now it acted as an acid. Both of these compounds can either accept or donate a proton, and therefore are termed amphoteric. We now have an A+ on our homework. Please turn it into the basket so I can give you credit.